In this video, we're going to talk about some of the disaster stories of security hazards and coding flaws that have occurred in Ethereum's history. Even though Ethereum's only been around for a couple of years, if you read any of the news articles about Ethereum, a lot of the most common and widely publicized articles are basically disaster stories where flaws or coding mistakes in smart contract programs on the Ethereum blockchain, though it happens in others too, have led to significant amounts of money being lost or stolen or stuck in some way. And so, one of the ways of understanding how to prevent these kinds of errors in the future is to learn from them. They also make for pretty good stories, so I'm going to tell you about a few of the most high profile and informative instances of this kind of problem. So let's warm up by talking about the King of the Ether Throne. This was one of the first smart contract bugs that caused some monetary loss. And this occurred during early 2016. So King of the Ether Throne was a gambling game. So one person randomly would win a jackpot at every given turn. Now, to illustrate what happened, let me just give this snippet of a pay winnings method. It's sort of like the one that was in the King of the Ether Throne. So this method can be called by anyone. When it's called, it has the effect of sending the current jackpot to the current winner and then clearing the current winner so that someone else can win in the next turn. Now, this would be fine if people just used public keys, like ordinary public key addresses, but like we talked about, in another video, it was common for people to use multi-sig contract wallets, even in early 2016. Now, if you didn't just use an ordinary public key address, you used a smart contract address, then when this instruction got to the send instruction, and this is especially, this was the case for the version of Solidity at the time, when it would call send, this would have the effect of invoking the fallback method in the multisig wallet contract. Now, the send instruction of Solidity at the time would send a minimum amount of gas, like 2300 gas. That's not enough to do very much. Not enough to emit an event, for example. And so the contract wallet, if the fallback method did more stuff, it took more operations or it emitted a bunch of events or kept track of the balance that you were storing, then it would end up running out of gas. It would consume more gas to receive the jackpot than the send jackpot instructions would provide to it. Now, what that means is that when it runs out of gas, it returns control back to the King of the Ether Throne game. However, the send instruction, and again, this is true for Solidity version at that time, the send instruction wouldn't throw an exception or return any error. It would just return 0, but the statement didn't check the return code, so it would just keep on executing. Including, in the next line, it would have the effect of, even though the send failed, it would clear the winner anyway, in which case the payment wasn't sent, but the winner no longer has the chance. They lost their opportunity, and that transaction would complete. So the net result is that if you used King of the Ether Throne and you were the winner, and you tried to go claim your winnings using your multi-sig wallet, you would inadvertently destroy all of your winnings. And that's what happened at that time. Now, there's a really interesting post-mortem on the King of the Ether Throne website that they released that basically explained what all of these concerns were. And I think the most interesting thing about what they showed was that they explained that even though they did fairly extensive testing and auditing of their contract, they had only done testing with ordinary public keys. They never had done any testing with these multi-sig smart contract wallets, so they never encountered the kind of scenario that would ultimately end up causing failures like that. So for the next one, we're going to talk about two different disasters that both affected the same Solidity smart contract, which was the Parity multisig wallet. So the Parity multisig wallet was a particular instance of a multisig wallet that would be installed by default. It came along with the Parity Ethereum client. So this was pretty common to use because it came with one of the default came as a default contract with a popular piece of software. Now, this one's a little bit more subtle because I have to explain a particular design decision that the Parity multisig wallet would make. So this idea is based on having a library contract code. So when you create a contract, you have to pay a gas fee that depends on the number of bytes of your program code. And so for every user who would create their instance of the Parity multisig wallet, they have to upload to the Ethereum blockchain some number of bytes. So in order to make it so that it would reduce the number of bytes in the contract that each user has to upload, they factored out the main functionality of the program code into a wallet library contract. And so all of the important code would be on the Ethereum blockchain once at a well-known address. You can actually go click on this link and see it on Etherscan still today. And each user, when they would upload their newly created Parity multisig wallet, they would just upload an instance of some very lightweight shim code that basically just relies on the wallet library contract to do all of the hard work. So it would have hard-coded into it the address of the wallet library, and each one of its methods, like its constructor method, a withdraw method, all the different methods would refer to the wallet library contract to run. Now, what this would actually use is a delegate call instruction, which is a fairly obscure instruction that was added to the Ethereum virtual machine sometime after Ethereum had already launched. It wasn't even in the original version. And so, for example, what would happen with the constructor would be when this per user wallet instance, the constructor is run, it takes in the owner of this wallet as a parameter, as an address parameter. It would actually use the delegate call instruction to call the init wallet method, which is defined in the wallet library contract, and it would pass the owner along with it. Now, delegate call is a little bit of a weird instruction, so let me try to explain this. What delegate call does is it runs the code of the library function of the library contract that you're calling, but it runs that code using the storage, the member fields, the balance, anything like that, of the original contract that is doing the calling. So in this case, the wallet library code is the object of delegate call, so all of the code from wallet library starts running, but it runs in the namespace of this wallet instance. So for example, when the init wallet method over on the right assigns the value to owner, that actually has the effect of assigning to the owner field of the wallet instance defined on the left. So that's a little bit subtle and tricky. It's not too intuitive. And actually the fact that this is unintuitive and not common in other programming languages may be an explanation for the problem that I'm going to explain in a moment. Now, one other feature of this method of this wallet instance is that the default function, the function with no name that gets called for a send instruction, for example, this would also delegate to the wallet library contract. And you would pass in whatever was the entire set of data would be passed over to the wallet library contract. Now, here's what happened. It was possible for an attacker to exploit a vulnerability with the default function of the wallet instance. So basically, if the victim included a method, like a call to a method, like to the init wallet method, because init wallet was not actually defined in the wallet instance, this would fall over to the this fallback function. Right, because init wallet isn't defined in the wallet instance, an attempt at calling init wallet would go to the fallback function, which would have the effect of calling delegate call on the wallet library. However, because wallet library has the init wallet method defined, this would allow the attacker to basically reinitialize the wallet instance. When this init wallet gets run again, it actually has the effect of assigning the attacker's address to the original owner, overwriting whatever was the original value of the owner of the contract. So this is an extremely subtle attack because it relies on several different kind of complicated functionalities of this. For example, realizing that the init wallet method isn't defined in the wallet instance code, only in the library, and realizing that by calling init wallet again, you'd be able to reinitialize and overwrite the owner field. So what happened was this was only noticed once an attacker actually started draining all of the ether out of a large number of instances of the Parity multisig wallet. Again, it was a best practice to use a multi-sig wallet of some kind for storing large amounts of ether, and in fact, many ICO projects that had raised a lot of money into their multi-sig wallets ended up being affected by this. So still today, at least at the time of recording this video, the address that whoever was the attacker that exploited this vulnerability and redirected all of this ether to themselves is still left idle. It hasn't been withdrawn to any exchanges. The attacker hasn't gotten away with it. So if you go visit this this address on Etherscan, you'll see that Etherscan lets you know that they think that this is an address associated with an attack. And at some time, this was $40 million. I don't know what the current price corresponds to now. So this, as I mentioned, this vulnerability is really the result of several kind of subtle things together. Any one of these things being different would have made this not as easy to exploit. So for example, the easiest way to fix this vulnerability is to modify the init wallet function so that you can't call it multiple times. After the constructor runs, it'll have the effect of setting initialize to true, and then if an attacker tried to exploit that feature to call init wallet again, it just wouldn't have any effect the second time because it had already been initialized. So this is exactly the fix that Parity did after this July 2017 bug, and so this is the new library that has that fix installed. So the story doesn't end there. As I mentioned, there were two security vulnerabilities, one after another, that both affected the Parity multisig wallet. So just a few months after the previous problem in July, some previously unknown character, DevOps199, posted an issue on the GitHub page for Parity, saying that he accidentally destroyed the wallet library contract. He explained that he was actually able to make himself the owner of the contract and then destroy it because it had not been initialized. So let me describe what was happening here. So as I mentioned, explaining the wallet library contract, the intent of which is to be called by a delegate call. Actually, this instance of a wallet library is itself just an ordinary contract. So even though under typical usage you would call it with delegate call from the instance of a wallet contract, it's actually a first-class contract itself. So it actually has an address owner field that had never been set. Now, even though each wallet instance has a constructor, the wallet library never defined a constructor. The wallet library would define an init wallet method, which would be called by the constructor of a wallet instance, but no one had ever called init wallet on this wallet library contract except in the instance of delegate call. The end result is that the owner field had never been initialized, and in fact the initialized field had never been set to true. So it was actually very trivial to take ownership of the wallet library contract. The attacker would simply invoke the init wallet method directly, not via delegate call, just calling it directly, and by doing so they could assign themselves to be the owner of the wallet library. Now, by being the owner of the wallet library, they were able to effectively destroy the contract. The wallet library had a method in it that you could use to terminate the contract instance, and so the attacker was able to call that method on the wallet library itself. Now, what's the net effect of that? All of those wallet instances, which would do delegate call to the wallet library for all of their functionality, now would essentially encounter a dead contract. It would immediately throw an exception whenever one of those wallet instances tried to call it. Now, as a result, any of the wallets that were running that code at that time are simply stuck. Any of the funds that are in them are not able to be used. At some time, at the time that this happened, that added up to about $152 million worth of ether that are stuck. There's a website, Parity Multisig Freeze, you can go to see the current status of this. Now, what's interesting is that in this story, no one knows who this DevOps199 character was. He explained that he was just a newbie and was experimenting with transactions on the Ethereum blockchain. We'll never know for sure whether this was actually just an accident or whether it was something done maliciously by this character. He's since deleted his GitHub user, and we've never heard from him since. So as a final story, let me tell you about the DAO and the security vulnerability that affected that. So the DAO was the result of a company, Slockit, which it started out as an Internet of Things plus blockchain kind of idea. They had a really interesting demonstration at DevCon where they would use an Ethereum transaction to unlock a smart home automation door lock, which was monitoring the Ethereum blockchain and waiting to receive a signal from a base station that a transaction was paid to the owner of the door that you could use to unlock the door. So they envisioned that tools like this would be useful for building a kind of blockchain-based Airbnb alternative. And they had a bunch of other ideas for things like bike locks and different kinds of things they would build in the same kind of idea. Now, rather than just go and raise money in Silicon Valley like ordinary venture capital, they decided to use the Ethereum blockchain in a more generic way to basically build their own fundraising and investing system. So they called this the DAO, which is after an idea, the decentralized autonomous organization, which shows up as early as prior to the Ethereum white paper. And the idea is basically to have, I think of it as a decentralized hedge fund. So basically, you're a decentralized investment company. So people would contribute to the DAO, deposit some Ether, and in return they would receive ERC20 tokens, which represent a portion of ownership or a portion of membership in the DAO. And the DAO smart contract had all of this logic in it that would basically take votes to authorize decisions by the DAO contract to spend that Ether. And you would get to vote in this decision making, you would get to vote in the smart contract in proportion to the number of DAO tokens you had, which corresponded to how much Ether you had deposited into the DAO. Now, they put a lot of thought into various kinds of game theory mechanisms, so it was actually quite a complicated smart contract system. In particular, they were concerned about the idea of a hostile takeover attack. And so they, which is where someone would just invest more Ether than anyone else had in the DAO and then control the vote and basically vote for themselves or vote for their own awful project so they could take all of the Ethereum away for it. So what the DAO contract implemented was a bunch of complicated mechanisms that would allow you to split, basically to take your share of the DAO and split off into a separate company, sort of like having a company split into two different ones. Okay, so all in all, it was a fairly complicated smart contract with all of these different mechanisms. The DAO was one of the first really successful ICOs that took place on the Ethereum blockchain, and so even though this was run as basically an auction, an ICO sale on an ERC20 sale on the Ethereum blockchain for just a couple of months, basically, they were able to raise around $120 million worth of Ether at the time. Now, people analyzing the DAO came up with a bunch of concerns about it, so there's an interesting blog post essentially pointing out that there were game theoretic flaws in the voting structure of the DAO. Basically, that people wouldn't really have an incentive to ever vote no on any proposal, even if you disagreed with it, because you could always split later as long as you hadn't voted yet. However, that concern ended up being not the thing that ultimately brought down the DAO. It was something a lot simpler along the lines of a coding error. And so again, this is something where no one noticed that this was vulnerable to the attack until it was realized that an attacker was actively removing Ether from the DAO using a mechanism that it didn't seem initially it was vulnerable to. Now, let me illustrate the problem of the DAO again with a sort of simplified contract here. So this is essentially a simplified form of a kind of ERC20 token contract you might see. So this contract has one member field, which is a balances mapping, and it maps each address of a member of the DAO to the amount of shares of the DAO that they currently have. Now, because these are supposed to be backed by Ether, this would have something like a withdraw method where if you had a balance of ownership of the DAO, you could withdraw your portion of the Ether from it. And what this kinds of code would do is it checks that your balance is actually greater than the amount that you have put in. If so, it uses a particular idiom to call basically to transfer the amount that you're requesting to whoever is calling it, and then it decrements the balance that you had. So this looks on the face of it like it's okay, but let's go into what's the problem with this. Well, let me first illustrate what the ordinary case would be if you had used a wallet contract. So if you used a wallet contract, you would actually have to call the withdraw method from within your wallet contract. So here I've got an example of like do withdraw. This tries to withdraw 100 Ether. So just to illustrate it, let me give an example of an ordinary usage of this, assuming that you were calling this from a wallet contract, just like in some of the previous examples. So here, one user has 100 shares in total. This contract has 300 shares and therefore 300 Ether. And let's say that we're actually going to call this method doWithdraw that has the effect of withdrawing the entire 100 shares. So naturally, this call to token.withdraw is going to go call the withdraw method. Because we actually have that much amount of money, it's going to do this call.value idiom. That's going to call the fallback method, which is going to emit an event, money received. And this is going to show that we've now received 100. And after this function returns, it goes and it removes 100 from the balances mapping. All right, and so at this point we're done. Our wallet contract has the 100 Ether. The DAO contract has gone from 300 to 200, and the balances mapping now shows that I no longer have any shares of it. Okay, so what's the problem? Well, let's look at an example where an attacker takes place. This is very close to the attack code that the actual attacker of the DAO had run. So the idea is that the attacker initiates the attack by calling this method once. But now the default fallback method, when that ends up being activated to receive this money, instead of just emitting an event or returning white array, it actually makes another call to the withdraw function. Now what's happening is that the call method has already transferred 100 Ether to the attacker's contract, but the balances mapping hasn't had 100 subtracting from it yet, because that only occurs after the call has completed. So now we've essentially gone another entry in the call stack. We've called withdraw again, although when withdraw goes to check that the balances is still greater than the amount that we're asking, because the balances mapping hasn't been decremented yet, this condition is still the case. As a result, we get another 100 Ether that is sent to the attacker's contract, right? Which means now the DAO contract here only has 100 left. And this function calls withdraw again. It just goes around in a loop. And every time it goes around, we still haven't subtracted anything from the balances field, even though we're leaking money. Eventually, at some point, it can't go any further because there's no balance left, or it runs out of gas, some kind of condition like that. However, just like in the case of King of the Ether Throne, where the send value wasn't checked for a return code, here the outcome of this isn't checked either. And so even after this fails, it just goes around, and each time it eventually unwinds the call stack, subtracting 100 each time these functions complete. The balance eventually goes negative, but at this point it doesn't matter anyway, because all of the money has gone from this token contract, the DAO contract, to the attacker. All right, so this is called the re-entrancy hazard, and it really only became well publicized once this was actually exploited in the DAO smart contract. Now there's a lot more to this story. We'll include a link to some material you can read to get the rest of it. Basically, the attack was carried out over a 24-hour period due to very peculiar reasons having to do with the splitting functionality. The attacker's funds were stuck for a 40-day period. This led to an intervention effort, a hard fork and a soft fork proposed by the Ethereum developer community. Um, there's a lot more to this story, and it's quite interesting. It involves white hat interventionists that actually tried to race the DAO attacker to drain funds to prevent the attacker from getting it. So that story goes on quite long, but it's all very interesting. So we'll include some links to the rest of that story. So what exactly have we learned from all of this? Well, it's a little bit difficult to say. It's basically a good thing that even in the fairly short period of time that Ethereum's been around, we've actually seen many examples, actually as real hard-won lessons of the consequences of bugs in smart contract programs. Each one of these high-profile disasters has at least been something to learn from, and in fact, the Solidity programming language has been frequently modified, and the Remix IDE and the output of the Solidity compiler basically include lots of warnings now when it looks like you're about to make one of the mistakes that has been made and led to some kind of disaster previously. It's interesting that not all of the attacks necessarily have to be actively exploited, like the King of the Ether Throne just happened automatically, not even as a big accident, it would just happen through ordinary use. One of the first parody wallet bug was clearly actively exploited deliberately by an attacker, whereas the one being So what exactly have we learned from all of this? Actually, each one of these circumstances was a little bit different. The King of the Ether Throne scenario happened, the problem would occur just through ordinary use due to the bug. In the case of the first parody wallet attack, this was clearly a deliberate attack, as it was quite difficult to take advantage of, required an attacker's effort. The second one, where all of the parody wallet library got destroyed by that DevOps guy, well, it's plausible that it could have been an accident, but we'll never know whether DevOps actually did it deliberately. And with the DAO attack, it was also clearly an attack that took place deliberately. So each one of these cases, it's interesting that so many high-profile cases have affected Ethereum even just in its fairly short time period. Each one of these has basically a lesson not to do that. Every time that such an event occurs, it's led to some kind of change in the Solidity programming language. The Solidity programming language now is a bit more careful. It's a little bit more difficult to make the mistake of having the send instruction return silently without throwing an exception that you wouldn't catch. Also, the Remix IDE has a lot of compiler warnings that show up. Each time you see a compiler warning, you may be tempted just to click through it or ignore it because your program can still run even if the warnings are there. But each one of those warnings basically corresponds to some lesson that was learned the hard way of potential for failure in smart contracts.